Hey everyone, welcome to InsightsByRish. Today's video we are going to implement a project of sarcasm detection using hierarchical BERT. Now actually this is a very different approach from the traditional conventional BERT that we know, because this project is purely based on the idea taken from this particular research paper. This is a research paper of a novel hierarchical BERT architecture for sarcasm detection. I will provide the link of this research paper in the description box. Go through that. You can see that they have implemented a sarcasm detection project with a very different approach of, and by hierarchical BERT what I mean is they have combined the BERT embeddings along with the LSTMs and the CNN layers. Now this is the proposed architecture that they have in this particular research paper. As you can see, by this architecture they have built this particular project, and hence I've also tried to incorporate this particular architecture of model in my implementation as well. Now they have also mentioned in this particular paper that which dataset they have used here, and like it's a Twitter dataset and the Reddit dataset. But in this project, we are going to make use of this particular dataset of sarcasm on Reddit, which is quite a large dataset. It consists of 1.3 million labeled comments. It's actually a binary classification problem where either the comment will be sarcastic or it will be non-sarcastic. So 0 label displays that the comment is non-sarcastic, and the 1 label demonstrates or symbolizes that the comment is sarcastic. So we have 1.3 million such data present in this particular dataset. So starting with, as we go along and as we go move further, I will try to explain you the architecture of this particular model as well as the steps that they have included into this particular architecture. Starting with, I have already loaded this kaggle.json file in my Google Colab environment, and I will load this dataset from the Kaggle here in the Google Colab environment using the API. So we'll start by validating the file. Now in my many previous CNN implementation videos, I've already demonstrated that how we can import the dataset from the Kaggle directly into the Google Colab environment using the API key, and hence I won't waste much time here explaining that. So let me directly start by validating the file. So directory, then p Kaggle, this is the name of our file, and then again kaggle.json, then in the Kaggle. Particular code validates our kaggle.json file that we have here. After that, we have to load the dataset here. So let me just copy the API command from here, and we will paste it by preceding it with an exclamation mark, and the data will start getting downloaded into this particular Google Colab environment. So once you refresh this environment, you can see now we have a zip file here. Now the next task is to unzip this file. So let's say here, extracting the zip contents. So in this particular cell at the top, we will include all the libraries here. So let me say here, importing dependencies, or we can say libraries. So first we require zip file here. So import zip file. By using this module, we will try to extract the zip contents here. Here I will say zip reference is a zip file, and here we will paste the path of zip file. Let's copy it, and then we also have to give the path where we have to paste all this extracted contents. So let me say here zip reference dot extract all, and we are going to store all this extracted contents in this Google Colab environment itself, and hence I will give the path as content, and then I will close this reference dot close. Let me run this. After running this, once you refresh the Google Colab environment once more, you can see all the data has been downloaded here. So we'll start building the dataset now. Let me say here cf pd.read.csv. Now we will require pandas library here, so let me import it. Pandas. So here I will import the required file. Now all these files have been downloaded here. Out of this, we require the train balance sarcasm CSV. So I will copy the path, will paste it here. Let me also display the first 5 rows of the dataset. So as you can see, this is your entire dataset where you have many columns. But out of this, we are just going to make use of 2 columns, which is label and the comment. We are not going to make use of other columns here because they are very irrelevant to our topic structure. we'll just go ahead with the label column and the comment column. This comment will be our input and the label column will be our target. So you can also check the shape here. Let me say df.shape. As you can see, there are 10,10,000 rows in this particular data set. Now this is very heavy to process, and hence I'm just going to make use of 10,000 rows from this entire data set. If you want, you can go ahead by processing this entire data set, or if you can, and if you want, you can even make use of 50,000 rows or 75,000 rows and something like that. But to make it simple, I will just make use of 10,000 rows, the first 10,000 rows basically. So let me say here df is equal to df 10,000. So what I'm doing here basically is, this df is new data frame, while this df is the existing data frame that we have here, and I'm just trying to include the first 10,000 rows from the existing data set into our new data frame df. Fine. And then again, I only want the label and comment column. I don't want to include all other columns here, so I will just remove the unwanted columns here. Let me say df is equal to df, and from this data frame I will just include the label column and the comment column. Fine. And then let me again display the data set here. Let's run that. As you can see, now we just have our required columns. Now if you check the dimension here, let me say df.shape. You can see now we have 10,000 rows and 2 columns. Now we will check for the null values here. So let me say df.isInit.sum. So we have just a single null value in the comment, and hence we'll just drop it, because out of 10,000 rows, if you are dropping just a single row, that won't make any difference. So let me say df.dropInit, and then let me say int is equal to true to make these changes permanent. And then I will again try to display the number of null values. Fine. So now we don't have any null value. Now the next thing that we want to do is, in the comments, it might happen that we have different types of data. Like in a single comment, we might have the string data, as you can see here. Then we might have some numbers into that particular comment. We might have some symbols into that particular comment. So it's necessary to remove all those unwanted symbols and numerals from our data, because as we are trying to detect the sarcasm, we can't make use of any numbers or any symbols here. So now what we are going to do, by using the regular expression library, we are just going to keep the string data here, or we can say the characters here. But if there are any numeric values, or if there are any symbols in the data or in the comment column, we are going to remove that. So let me say here, removing unwanted numerals and symbols. So I will say df comment. I'm going to make the changes in the same column. If you want, you can create a new column for that. So here I will say comment, the column from which we want to remove the numerals and symbols. Then I will say string dot replace, and what we are going to replace here is basically, we are going to detect the characters apart from the small a to z, that is the lowercase a to z and uppercase a to z. And if we detect any such characters apart from the lowercase a to z and uppercase a to z, we are going to replace it with a space. So let me say here r, and the regular expression for this is upper arrow and then small a to z and then capital A to z \s, and we are going to replace it with an empty value, or you can say space. And then let me say regex is equal to true. This basically stands for regular expression library, which helps us to remove all those unwanted characters. And let me run this. After that, the next thing is again, we want to convert the case of data. As you can see here, into this particular comment, we have the lowercase as well as we have the uppercase data. We are going to convert all those data in the lowercase. Now it won't matter much, because we are going to import the uncased BERT model from Hugging Face, so it won't make any difference, but still it's better to convert the data into the lowercase. Let me say here, converting the data to lowercase. So here I will write a function for that. Let me say def lowercase, and here I will pass the text that will be individual rows from the comment column, and then I will return the text dot lower. So let me apply this function on the comment column. Again, you can create a new column for storing the transform data, but I will save the or store the transform data in the same column. And then here I will say apply this lowercase function. Fine, let's run this. Let me again try to display the data frame here. Now you can see you don't have any uppercase character. If you take a look at the previous data frame, you can see the first letter of every comment was capital, but now it's in lowercase. After doing that, after performing all this data cleaning and data pre-processing, next thing is to perform tokenization. So let me write here second task of tokenization. Also the first task was here data pre-processing or data loading processing. Fine, so we'll go ahead with the tokenization. Now as we are going to work with the BERT model, we want to import the tokenizer for the BERT model itself. So because there are multiple tokenizers available on the Hugging Face, but we are implementing the BERT model, hence we will import the tokenizer for that particular model. So let me import it here. Say from transformers, will import the BERT tokenizer. Let me run this. So going back to the tokenization part, let me say here tokenizer. Here I am just going to import the model, nothing else. So let me say BERT tokenizer that we have imported, and then from pre-trained the BERT base uncased model. BERT base uncased. Now what we mean by this basically is we have two types of BERT models available. One is BERT base and another one is BERT large. Now in BERT base model we have 12 encoders stacked on top of each other, and in BERT large we have 24 encoders stacked onto each other, and that will be very huge model for this small pre-processing. Hence we are going to make use of BERT base, where we have 12 encoders stacked onto each other. And uncased basically means it won't make any difference between the lowercase and uppercase data. Now we have already converted all the data into lowercase, still it's better to import the uncased model. So this was the tokenizer. Let me run this. Here we are just importing the pre-trained BERT tokenization model, nothing else. We have to write the function for tokenization furthermore. So let me write here the tokenization function. This is, or we can say function for tokenization. So let's write a function. We'll say def tokenize data. Let the function name be tokenized data. Here we will pass our text, that is every input or we can say every individual row from the comment column, and then the maximum length. We also have to specify the maximum length of sentences that we can take. So let's say if you are saying that your maximum length would be 100, let me say here this is a default argument. So maximum length we are saying 100, which means in every sentence or every comment should have 100 words each. Like in the first row we should have 100 words, in the second row we should have 100 words, not more than that, not less than that. Fine. Now wherever we will have less number of words as compared to 100, we will be adding the padding tokens, and where we will have the number of words exceeding the maximum limit 100, there we will eliminate the ending words. So the maximum length is 100, and here we will return. And what we are going to return here is we will say return tokenizer. A tokenizer is the variable in which we have loaded our pre-trained BERT tokenizer, and in the tokenizer we will pass text to list. We are converting the text to list. Then the maximum length would be the maximum length. Now this maximum length is the inbuilt parameter, and this maximum length is what we are passing from here. Let me paste it here. Fine. Or you can directly say here maximum length as 100, even that will do, but we will go ahead with this particular syntax. After that we will say truncation is equal to true. So by that what we mean, as I said previously, if you have the number of words in a sentence exceeding the maximum length, let's say in a sentence you are having 150 words, but the maximum limit or the maximum length is just 100, then it will be truncating that extra 50 words. That is, it will be removing or eliminating that extra 50 words to match the maximum limit. And after that we will say padding. Padding is equal to, we will give the maximum length. By this what we mean is, let's say you have number of words in a sentence less as compared to the maximum length. Like we have 70 words in a sentence, so the maximum length is 100. So it will add 30 padding elements in your sentence in order to make the maximum length of a sentence to 100. So after that, then we will return, let's say return tensors is equal to NP. Now if you say here TF, that is instead of NP, if you say TF, that is you are returning the tensors in the TensorFlow format, what will happen is you won't be able to perform the train test split, because basically the train test split expects the data in the form of NumPy or in the form of data frame, like the NumPy array or the data frame format. But if you say the return tensors are TF, then it will be in the form of TensorFlow, and your train test split won't accept that. Hence you will be returning the tensors into the NumPy format. Let me say NumPy. Okay, so that's all. This is the function for tokenizing the data, and now we have to apply this function on the comments. So let me say here tokenize data equal to, let me call the function tokenize data, and here we will pass our comment column from the data frame df. Let's run that. Now if you want, you can even see your tokenized data here. Tokenized data. As you can see, your input indices, this is your tokenized data, and wherever you can spot this 0, these are the padded tokens that you have applied. So so as I said previously, wherever the number of words would be less compared to the maximum limit, there we have added this padding elements. So wherever we have this 0, that basically means that we have added the paddings. And then we have the attention mask. So we have these two important features in our tokenized data. One is input indices IDS, and the second one is attention mask. Now, attention mask just is in binary in nature, 0 and 1. 0 means the tokens are not padded, and 1 means the input is padded. That can easily make you identify, because when you're processing the data, the sentences or the inputs that have the padded elements won't be that relevant because they have some unwanted data. But the sentences or the inputs that don't have any kind of padding, that will be more relevant as compared to the other ones. So wherever the attention mask is 0, that is the input is not padded with any kind of padding elements, then that would be given more preference as compared to the attention mask where the value is 1. Fine. After this, let me hide this. So here we are going to perform the train test split. Say here train test split. Now for this, again we require a library here. So let me say from sklearn.model selection, we will import train test split. Fine, let's run that. After doing that, let me come back to this particular point. Now we will create two variables here, x and y. In this x we will have our input data, and in our y we will have our target data. Now here we will say, now input data won't be the comment column from the data frame, because that's the raw data. We have processed it, and we have generated the word embeddings, positional vectors, input indices, and all those stuff for that particular data, and that data we will pass here in our input. So let me say tokenized data. This tokenized data is what we saw here. Okay, this is the tokenized data, and from that we won't be passing the attention mask here in the input for train test split. We will just be passing this input indices. Fine. So let me say here input IDS. So from this, like we have, as I said previously, we had two important features in this tokenized data. One is input indices, and the next one is attention mask. From this, we are just passing the input indices from the tokenized data in our input variable. and in our y we will pass the label column from the data frame. Fine. So this is what we divided our data set into the input portion and the target variable portion. After that, we'll perform the train test split here. So let me say x train, then x test, y train, and y test. Then the train test split module that we have imported, and here we will pass our input data that is present in x and the target data which is present in y. Then the test size, let's say 0.2, that is 80% data in the training set and 20% in the testing set, and then random state is 42. Let's run that, and let me display the dimension here. Let me say x train dot shape and x test dot shape. Initially we had 9,999 rows. That's because initially we converted our data, or we extracted 10,000 rows from the original data frame, but then we had one null value in the comment column, and we deleted that particular row, and then we were left with 9,999 rows, out of which 7,999 rows are present in the training set and 2,000 rows are present in the testing set. Now this 100 doesn't mean columns. Fine, 100, you might think that in this particular original data set we just had this many columns, but then how after train test split we have 100 columns here? Because this 100 doesn't specify or doesn't demonstrate, symbolize any kind of columns. 100 basically means that in every sentence we are having 100 words, or the length of every sentence is 100. As you can see here, the max length that we have given is 100, and that's why we are having the shape on the y-axis as 100. Fine. After that, we will start building the model according to the approach given in this particular research paper. Let me say here text, building the model according to the proposed architecture. Let's run that. Now, to build the model according to the proposed architecture, first it's necessary for you to understand the architecture which is given in this particular paper. Now if you go through this paper, you can see in this approach section they have clearly specified every little detail. They have also demonstrated the architecture here. They have literally gave everything about how to implement the model, and there will be 5 layers that you would be adding in your function to process the input data. First would be the sentence encoding layer. In this you would be encoding your input data to a fixed size vectors, and then there's description about that. You can go through this. Then you have the context summarization layer. In this particular layer, what you will do is the sequence of embeddings that you have achieved from this sentence encoding layer, you will try to convert that individual sequences embedding into a common single vector. And by that what we mean is, as you know, we are summarizing the context. Fine. After that, we have the context encoder layer. In this, what we will do, we will try to implement a bidirectional LSTM to capture the temporal dependencies from the summarized sentences. And why we are making use of bidirectional LSTM is because it will process the data in both the direction, the forward direction as well as in the backward direction, which will make it very easy to capture the temporal dependencies and to summarize the data. After that, we will also make use of CNN layers here. Now what the CNN layers will do, it will try to extract the local features from the encoded context vector. This context vector, or you can say the context encoder layer, whatever the output it will produce, it will be further passed to the CNN layer. Then it will try to extract the local features from that particular encoding layer, and it will try to emphasize more on the significant features that are relevant to your model, and it will give very less attention to the irrelevant features. Fine. And at the end we will have the fully connected layer that will be used to process our entire complex interaction of the that we have between the data. Fine. That will be our last layer, and this all stuff they have also proposed in this particular architecture. So as you can see here, you can see whatever I said is shown in this particular architecture. You have different sequence encoders where we are taking the input of various data. Then we are trying to represent that. We are trying to aggregating all the individual sentence inputs that we have gathered, or we have trying to aggregating all the context here, And then we are passing that aggregated context further to the convolutional 2D layer, which is a sentence summarizer, which will try to summarize the sentence. By that, what we mean is it will try to combine all the individual input embeddings into a single vector, and it will give more focus to the relevant features, and it will try to give very less attention to the irrelevant data. Now, one thing you have to keep in mind is they have used convolutional 2D network because they had that much of data. As you know, they have 1.3 billion of data, and that's quite large. So that they had that kind of efficient data and a large data set, and hence they made use of convolutional 2D technique. But here we are just working with 10,000 rows. As I said previously, we have extracted only the first 10,000 rows from the data set, and hence we will make use of convolutional 1D network, not 2D, because that won't give us the desired output. It will be saying, it will throw an error basically that the data is not enough. After that, you will have your LSTM layer here, where you will have n number of LSTM units. Then you will have the convolutional 2D kernels here. Again, we will make use of convolutional 1D kernels and not 2D. And then at the end, we will have the max pooling to extract the important features, to aggregate, to perform averaging. And at the end, we will have our fully connected dense net. So this is the proposed architecture. We will try to implement this now in our particular model. So going back, we will start by writing a class here. So let me say class hierarchical BERT tf.keras.model. Now for this, first we have to import the TensorFlow here. Let me say put TensorFlow as. Let me also import warnings here actually. So let me say import warnings because it gives a lot of unnecessary warnings in between. Fine. Now coming back to this, we will start building our hierarchical BERT here. So first will be your init method, of course. So let me say def init. Here we will have self, then we will have the BERT model. Now this BERT model is the variable in which we will be loading our pre-trained BERT model. We will load that in the next cell after writing this particular function. But just keep in mind that this BERT model will be the variable in which we will be loading our pre-trained BERT model from the Hugging Face. Then we will have our LSTM units. As I said, or already shown, that in this LSTM layer that we have after the convolutional network, you can specify the number of LSTM units that you want into this particular layer, and that we will be taking as an input. So the LSTM units, then the CNN filters. So there you can see the convolutional 2D kernels that we have, that kernels are also called as filters basically. So you can see that it's shown in the red, green and the blue boxes. So you also have to specify the number of CNN filters that you want, and then in the last fully connected layer, you also have to specify how many dense units you want. So let me say here dense unit. Fine. After writing this, we say super comma self dot. So this super method will be useful for us in the case of inheritance, where we want to extract some functionalities in our child class from the parent class. And then the first layer, as I said, is a sentence encoding layer. Fine. So as I already shown you in this research paper, the first approach in the first layer in the approach is sentence encoding layer. So we'll start by writing the code for that. So we'll say self.dense sentence is equal to tensorflow.keras. Then we'll say a dense layer here. So this encoding layer will be our dense network, in which we will have 768 dense units, and then the activation function as ArrayLU. Now as we are working with the base model of BERT, hence we are specifying the dense units as 768, because the BERT based uncased always has a dimension of 768. It depends upon what kind of model you are working with. So this was the sentence encoding layer. After that, you can see in the approach after sentence encoding layer, next we have the context summarization layer. So in this context summarization layer, we will be adding the pooling layer. That global average pooling layer, what it will do, it will try to convert that individual input embeddings into a single vector by which it will be summarizing the data. So let me say here self in pooling flow.keras dot layer, and we will be importing the global average pooling layer. Global average pooling. As I said previously, we won't be working with the 2D layers because that won't be able to handle this less amount of data, because our data is less as compared to the data that they have worked with, and hence we will go ahead with the 1D. So this was the context summarization layer. After the context summarization layer, the next approach or the next layer in the approach that we have is the context encoder layer. So let's say context encoder layer. Now, as I said previously, in this context encoding layer, we will be making use of bidirectional LSTM to capture the temporal dependencies in both the forward as well as in the backward direction. So let me say here self BiLSTM, that is bidirectional LSTM encoder, is equal to TensorFlow.keras.layers. Now here we will be making use of the bidirectional layer. So let me say here bidirectional. Now in this bidirectional layer, we will be passing our LSTM layer. So what we will say? We will say tf.keras.layers.LSTM. So in the bidirectional layer, we are passing the LSTM layer with the number of LSTM units. So whatever input that you give for the LSTM units, that will be passed here, and then the return sequence is equal to true. So this was the context encoder layer, which is making use of bidirectional LSTM to capture the temporal dependencies and the context from the summarized data that we are getting from the summarization layer. Fine. After the context encoding layer, the next task that we want to do is to build a CNN layer. As you can see here, after the context encoder, we have to make use of CNN layer to capture the local features. So let me go back to the code and we'll say here CNN layer. So first we'll be adding our convolutional layer. So self.convolutional tensorflow.keras.layers, and again we will add the convolutional 1D. Convolution 1D. In this we will passing the number of filters. So let me say CNN filters is equal to 2, and then the activation function as ReLU. And then after the convolutional layer, we will also be adding a pooling layer here. Let me say self.pool tensorflow.keras, and we'll add the global max pooling layer. Max pooling 1D. Everywhere we are just making the use of 1D module of convolution, and nowhere we are making use of any kind of 2D model. Fine. So we are done with the CNN layer as well. The last layer that we want to add into this particular code is our fully connected layer. That will be our last output layer, not actually output layer, but the last layer where we will try to combine and interpret the extracted features by the previous CNN layer. Like we have achieved some output from the CNN layer. That output will be further passed to the fully connected layer, and then it will try to combine and interpret the results from that particular output. So let me say here fully connected layer. Here I will say self.dense fully connected is tensorflow.keras. Here we will pass our dense units. Whatever input you are giving for the dense units will be passed here. Again, the activation function would be ReLU. So this is the fully connected layer, and after that we want to add our output layer. So here we will say self.output layer, and we'll say tf.keras.layers, and here we'll be adding a dense layer with just one unit, because we are working with binary classification module. Like the output, either it will be 0 or 1. So when we are working with binary classification module, the output unit or the output neuron would always be 1, because that will always give you the output either 0 or 1. And then the activation function. Now, as I already said, we are working with binary classification model, hence we will make use of sigmoid activation function here. So this was the init function. Now inside this hierarchical BERT class, we have to write one more function here of call. Now what is this function? This is actually a forward pass. Now if you want to understand the context of forward pass in terms of neural network, we basically try to apply various appropriate transformations on the input data to produce the output data. Now we have written all this code. We have written all, like we have included all the layers. We have included the units, activation functions, and all those things. But it's also important to apply all this stuff on the data that we are receiving as an input in order to produce an output. And for that, we will write this call function here. So let me say self, and we will receive some inputs here. Inputs would nothing but our, the tokenized data that we have from the comment column. So let me say here BERT embeddings. Now what are these BERT embeddings? It basically will be passing our input tokens to obtain the BERT embeddings. Whatever tokens that we have produced here will be passed here in order to generate the BERT embeddings. So let me say BERT output. A minute. Here I will say self dot. Now here we have to specify the pre-trained BERT model that we have taken as an input. So let me check what name we have given to that. I think, okay, so we haven't actually imported that. Let me say here self.BERT, and in this we will be passing the BERT model that we are taking as an input in this particular class. So we will be loading the pre-trained BERT model from Hugging Face in the BERT model variable, and then we'll pass that to the BERT variable in this particular class, and we'll pass that BERT here, and then it will take the input. So the BERT embeddings, the BERT pre-trained BERT model will be applied on inputs text 0. After that, we will be applying the sentence encoding layer here. So encoding layer. Here I will say sentence encoded self.dense. I think that was the name here. So self.dense underscore sentence. We copy it from here itself. And here I will pass this BERT output. Now this BERT output is basically the BERT embeddings that we have achieved from this particular code. Then that will be passed further to the sentence encoding here. Then let me write the context summarization. Now in this context summarization, we will try to apply that context summarization layer on the output that we have achieved from this sentence encoding layer. Fine. So let me say here context summarized, and here I will be passing this self.mean pulling from context summarization, and we will be applying it on the sentence encoded. This particular thing we will pass it here in the context summarization layer. So in this call, it's actually a forward pass. We are just trying to apply all the things that we have already loaded on our input data. Now after this context summarization, the next thing that we have to do before adding the CNN is we have to expand the dimensions, and I will let you know the reason in just a minute. So let me write here just expand the dimensions. Now why we basically require to expand these dimensions is the basic requirement of the LSTM is the batch size along with the time step, but here we just have the batch size and we don't have the time step, hence we have to expand the dimension. So let me say here context underscore summarized, we'll give the same name, and here I will say pf.expand dimensions. Here I will pass the previous summarized context and the time step as 1. That is, at every particular time step 768 single vector will be generated, or we will be processing 768 dimension vector. After that, we will apply the context encoder layer here. So let me say context encoder layer. Now the context encoder layer, as you know, it's the bidirectional LSTM, and hence before applying the LSTM layer in the bidirectional LSTM, we try to expand the dimension, because if we won't expand the dimension by adding the time step, before working with the LSTM layers, then it will basically throw us an error. So let me say here in the context encoded layer, context underscore encoded, and I will say self dot bidirectional LSTM encode, the name that we have given here to the encoder layer, and in this we will pass this context summarized. After performing context encoding, that is after working with the LSTM layer, we don't require that time dimension or the time step anymore. So we'll again remove that. Let me say here, squeezing the dimension. Because here we added that dimension, or you can say the time step, we expanded the dimension because we want to work with LSTM. But now we are done working with LSTM, and hence we'll remove that again. So let me say here context coded squeezed. We'll say tf dot squeeze, and in this we'll pass the context encoded that we have here, and we'll say access is equal to 1. So we have again squeezed the dimension that we expanded initially before working with the LSTM. Fine. After squeezing the dimension, now we will add the channel dimension. Now, as you know, after working with the bidirectional LSTM, that is after working with the context encoder layer, next we want to work with the CNN layer. But here we don't have any channel dimension to give to the CNN layer. Hence, we have to add the channel dimension explicitly before doing that. So let me say here, adding the channel dimension match required put shape by the convolutional layer. So here I will say context encoded expanded. Here I will say tf dot expand dimension. Again we will expand the dimension. We will say here context. We will pass this context encoded squeezed here, and we will again give the axis as -1. Fine. Now after adding this channel dimension, now we will add the CNN layer. So let me say CNN layer. We will apply the CNN layer basically here. So here I will say convolutional output. In this I will pass this self dot convolutional, that was the name of for our convolutional layer, and in this I will pass this context encoded expanded. Fine. After that we will say pooled output, and in this pooled output we will be passing this self dot pool from the convolutional layer, pass it here, and here we will pass this convolutional output. Fine. After doing or after working with the CNN layer, now we will try to build our fully connected layer. So let me say here fully connected layer. Now we will say dense output, and as we are working or as we are building the fully connected layer, it will basically be a dense layer, nothing else. So let me say the name for the fully connected layer that we gave in this particular init method, which is self.dense_df. Let me copy it from here, and in this I will pass this pooled output. We are just applying the layers onto the output that we are getting from the previous layers, and after that we will build our, or we can apply our output layer. Let me say final output is, and the name of our output layer was self.output_layer. I will copy it from here, and in this I will pass the output of previous layer, which is dense output, and then you will return this final output here, return final output. Fine. So this was the function for building all the layers that they have mentioned or they have given in the approach of this research paper. Now I know that this is a bit complex approach because they have tried to embed, or you can try to combine different things like the bidirectional LSTMs, CNN, again the LSTMs, BERT models. A lot of things they have tried to combine in order to produce an efficient model, and hence this approach is quite a complex one. Now, after writing this function, we have to load the BERT model. We have to load the trained BERT model, right? So let me go back to this. Here I will import it in this particular line itself, because we are importing it from the transformer models itself. So let me say from transformer import BERT tokenizer and TF BERT model. Let me run that. So going back, here I will say I will load that BERT model. Now this BERT model is a variable, as I said previously, in which we will be loading our pre-trained BERT model from the Hugging Face. So here I will say TF BERT model from pre-trained, and the name of our model is BERT base uncased. Let me write a comment here that loading the trained BERT model. Let's run that. So here we are loading the pre-trained BERT model from the Hugging Face, and the name of the model is BERT base uncased. I already told you about the significance of the word base and uncased here. After that, like, let the completion be done. After that, we will define the hierarchical BERT model, this function that we have written here. So let me say here, defining the hierarchical BERT model. So here we will say model and the function name, which was hierarchical BERT. Let me copy it from here. So I will pass it here. Now what all things we want to pass here actually? We want to pass the BERT model, then the LSTM units, the CNN filters, and the dense units. Fine. Copy it. Fine. So the BERT model, I have already loaded the pre-trained BERT model in the variable. After that, the LSTM units would be 128. Then the number of CNN filters, I will say 64, and the dense units would be 32. These are just the random hyperparameters. You can even change these hyperparameters to check their effect on accuracy. After that, let me run this. I haven't run this cell yet. So now it will work fine. So the issue is somewhere with the convolutional 1D layer. Here. So the 1D layer. Okay, fine. So it's comma not equal to. Fine. Now it will work fine. Let me go back to this code, and now when we run this code, it will work fine. Let's run this. Now we will try to compile it. So let me say model dot compile, and in this model dot compile we'll pass the optimizer first. So let's say optimizer equal to Adam, currently the best popular optimizer available. After that, the loss. Now as we are working with the binary classification problem, hence we'll pass the loss function as binary cross entropy, and then the metrics, like, depending upon what we are going to evaluate our model. Now here we are going to evaluate our model depending upon the accuracy, and hence the matrix is accuracy. Let's run that. So we are done with compiling as well. Now we will try to fit it. We'll say model dot fit. Here we will pass our X train and Y train and the number of epochs. So let's say number of epochs be 5. Always start with less number of epochs. So let's say number of epochs as 5, and the batch size, we will pass the data in batches, because we cannot pass the 10,000 instances individually one by one. So let the batch size be 32. Let's run that. So as you can see, after the completion of 5 epochs, the accuracy that we are getting is about 62%. And even if you try to check it on the testing set, so let me say here, loss, comma, accuracy, and we'll try to evaluate it on our testing set. Let me pass the testing set to external my test, and we'll also try to print that model's accuracy. So print model accuracy, and we'll also try to multiply it by 100 so that the accuracy will be displayed in the percentage format. Let's run that. So the model's accuracy on our testing set is 63%. So the accuracy on the training set was about 62%, and on the testing set it is about 63%. Now this accuracy, though it's just about 63%, but it can be considered as good because this model has been implemented with a very different approach than the traditional one. So we have used the BERT for sarcasm detection, that is for this particular project, but we have used a very different approach as given in this research paper, in which we are embedding various LSTM, CNN and bidirectional LSTM layers along with the BERT model. This can be considered as a good accuracy, and if you want, you can play with some hyperparameters. You can try to change some values of LSTM units, CNN filters, dense units, and even you can try to include more number of rows. So after doing all these things, you might find some difference in the model's accuracy. This was the project for sarcasm detection using the hierarchical BERT approach that we took from this particular research paper. So I will provide the link of this particular research paper, the dataset, in the description box. You can check that. So that's it for the video. Thanks for watching.